Whoa, did you see that?
That was nasty.
I think Mr. Scott let one go.
Oh,
We didn't
man.
even get to set the whoopee cushion up for him.
Clear the room out.
Gas laws. This is Gay Lussacs law, and this is the last one about pressure and temperature. Now we've looked at volume and pressure, and we've looked at volume and temperature. Now the volume is constant, so we don't need to worry about the volume.
So, Gay-Lussac's law basically says that pressure and temperature are directly proportional, so that if pressure goes up, temperature also goes up,
Okay.
and vice versa.
If the pressure went down, the temperature were to go down.
So again, we
Okay.
have another animation.
So if you're thinking about the molecules, pay attention to the thermostat. Thermometer? Thermometer. All right,
Sure.
redo. So if pay attention to the thermometer there, you can see it's heating up. The molecules are going to get faster because that's what temperature is.
So faster molecules mean stronger collisions with the sides of the container.
Which is pressure, right?
Exactly. So harder collisions, more force, means more pressure is being exerted on the container.
So they're moving faster. They're going to hit the container more often. So higher temperature, higher pressure. And then the opposite would be true. If we cooled them down,
They would hit the walls with less force, so less pressure.
okay, that makes sense.
That's Gay-Lussac's law.
All right, so one problem I have all the time is, how do you get an egg into a bottle?
That's a fantastic quandary.
It is, and Gay-Lussac's law actually answers that. Let's take a look at what happens here.
So in this demo, this person's soaking a cotton ball with some ethanol. Soak, soak, soak.
I struggle with this problem almost every other day. It's just, I have an egg and I need to get it into a bottle, so...
All right, lid on fire now. Lid on fire.
Oh, he made that look so simple. How did he do that?
That's a good question.
Well, it's actually, it's really simple. It's explained through Gay-Lussac's law. The fire that you see inside, you can see how it kind of bounces the egg up and down a little bit. That's actually the gas inside escaping, which is Charles' law, because when it heats up, it expands. So once the gas escapes, it'll keep doing that until all the oxygen inside is burned out. Then what happens?
I have no clue.
Oh, Mr. Castiglione's letting us down here. So when the gas escapes, there's less gas in there, so the pressure has to go down inside of the bottle.
The key is inside the bottle, all this happens once the fire goes out. Once the fire goes out, the temperature goes down, and according to Gay-Lussac's law, the pressure goes down. So how does that exactly get the egg inside the bottle if the pressure inside went down?
Well, the outside air, the pressure from that air pushes the egg so hard that it actually goes into the bottle.
So the outside air pressure is now stronger than the inside pressure, and it pushes it.
Just like the trash bag that we did in the classroom on sometime this week, probably.
Yes.
2 points me.
Excellent connection. So you could say this demo sucks, but...
What? No, science never sucks. This demo pushes.
Yes.
Here's a practice problem for Gay-Lussac's law. This one has to do with a scuba tank. If you have a scuba tank, if you're a scuba diver, maybe you leave it in your car. The air in the tank is under pressure. Here we have it in PSI, and about room temperature, pretty standard, 20 degrees Celsius. If you leave that in the trunk of your car, and you're in Florida, there's some good scuba diving down there, and after a few hours it gets to 53 degrees Celsius. Well, 53 degrees is pretty warm. The scuba tank is pretty rigid, so it's not going to expand. The volume is going to stay constant, but eventually at some point, if the pressure gets high enough, it could burst. So we need to know, at that temperature change, what's going to happen to the scuba tank. What's the new pressure going to be? So 20 degrees Celsius, we need that in Kelvin, 273. And that's going to give us 293 K. And we don't know what the final pressure is going to be, but we need to figure out if it turns out to be 130 degrees in Florida, at 53 degrees Celsius, it's about 130 degrees. We need to know that that scuba tank will not rupture. So it needs to be able to withstand the new pressure. That's going to give us 326 Kelvin. Okay? So Gay-Lussac's law says the temperature, as the temperature rises, the pressure is also going to rise. So that's what we're trying to do, make our pressure rise. I have 2,400 pounds per square inch, and my temperature ratio, to make it get bigger, I need the larger temperature on top, 326 Kelvin over 293 Kelvin. That's the ratio by which my pressure is going to go up. So my units will cancel out there, and my final pressure is 2,670 psi, or I only have two significant figures, so we need to say 2,700 pounds per square inch. And that's important when you're manufacturing the scuba tank, that you know as the temperature changes, it can hold higher pressures than what you put in it. It needs to be able to hold 2,700 psi. We can do another example. Gas in a tank has a pressure of 650 millimeters of mercury, 40 degrees Celsius. What is the temperature going to be if we raise the pressure to standard pressure? Again, there's no number there, but standard should wave a red flag in your head. My initial pressure, 650 millimeters of mercury. My initial temperature is 40 degrees Celsius, or 317. Oh, gotta get the pen back out. 313 Kelvin. My final pressure is standard. So what does standard mean? Well, that's 1 atmosphere, or any of the values on the back of your periodic table. This is in millimeters of mercury, so I'm just going to use the 760. It's already in millimeters of mercury. And I don't know what my final temperature is. Unknown. The pressure is going up, so my temperature is going to go up, and that's what we were trying to solve here. So I need to take my temperature, and I need to see how much it's going to go up. The pressures are going to be used in a ratio to make it go up. 760 millimeters of mercury over 650 millimeters, and that will give me a higher temperature of 365 Kelvin. But what is the question actually asking? It says, what is the temperature in degrees Celsius? What's that new temperature going to be? So if I have 365 Kelvin, I need to go backwards to Celsius. So if I subtract 273 from that, I'm left with 92 degrees Celsius. And the subtraction problem says there's no decimal places, so those two numbers are fine with no decimal places. 92 degrees Celsius.